Good afternoon, girls. So last week what we did indefinite integration, right? So what we all discussed was that the application of calculus, how calculus is important for us, and then we also dealt in the historical evolution of calculus and the thing which connect integral calculus and differential calculus. And then we did was that different integration, definite integration, indefinite integration is nothing but the reverse thinking of differentiation. And we learned that it is little difficult as compared to differentiation. It was because we had to do the reverse thinking. So now again we discussed many complications which we faced during doing integration problems, and then we started uh, seeing that how trig function is being differentiated and then anti-differentiated. Then we started how polynomial functions was differentiated and then anti-differentiated, and some famous trigonometric functions. And then we developed a result over that, and then we started exploring the various types. And last time we were doing the substitution. What was substitution? It was just a reverse thinking of not product rule, chain rule. It was a reverse thinking of a chain rule. Since you have told the word product, so first we will discuss what is a product rule. In differentiation, what we did in product rule, let's say I have a function y is equal to fx into gx, right? Now I want to differentiate it. So what does product rule says? First function into the differentiation of second function plus this was a product rule, right? This was product rule which we studied in differential classes, right? Now we will try to do a reverse thinking about it. Should I rub this? Now consider a function u v, right? Consider a function u is a function of x and v is also a function of x, right? And we know that d by dx of uv is nothing but u dv by dx plus, right? So we can say that d of uv is equal to u dv plus v du, right? And then we can say that u dv is equal to d of uv minus v du. Can we say this? Can we say this? Right. Now, let's say if I integrate both sides, I can do this way because the rule of integration goes with the difference, that the integration of a difference is difference of integration, right? Now we can say that integration of u dv is equal to integration of duv minus v du, right? So I'm going to simplify it further. So I can say that u dv, what will be the integration of d of uv? uv minus v du. So here the trade is, we have to see, let's say I have to integrate the function u dv, and I don't know how to integrate u dv, but it is very easy for me to integrate v du. So here is a trade, right? It appears to be difficult task for me u dv, but v du doesn't appear to me a difficult task. So I can trade it and I can find it, right? So whenever we are doing integration by parts, we have to think like if I have given you to integrate u dv, you have to think that okay, fine, u dv is difficult to integrate, but I can see that v du can be easily integrated. So I'm going to make a trade between u dv and v du. Understood? So now the challenging part is to identify, right? What to identify? Which is u and which is dv. That is the challenging part. You have to identify what is u and what is dv. So we'll be seeing in that. Okay, so we must be able to see what is. We'll be giving you the ideas how to identify which one to be selected as u and which one to be selected as dv. So the first question which we can see, the question number 14, is that show that the functions of x, ux and vx, integration of uv dx is equal to u of v dx minus u prime integration v dx. So how to prove this? How to prove this? I have something on the left hand side and I have something on the right hand side, right? Can I differentiate? Can I differentiate both sides? Right? If I differentiate the left hand side, what will be the answer? uv, because uv is of some function of x into dx, and that is integrated. So the definition of differentiation is the anti-differentiation. You know the connection, na? So if I'm going to differentiate uv dx, the answer would be uv. So left hand side is very easy to guess that, okay, my left hand side will be uv if I differentiate, right? Now, what about the first part, u of integration of v dx? So it is a product of two function, isn't it? It's a product of two function. And what does differentiation of a product rule says? First function into the differentiation of second function plus second function into the differentiation of first function. So let's say I have to differentiate u of uv dx. So I can say I'm taking u as constant and I'm going to differentiate v dx. What will be the answer? V plus I'm going to take v dx as constant. Agree? Now what is the second part? Integration of u prime into some integrable v dx. So basically this thing becomes the function of x which is being integrated, and I want to differentiate, so I will get the same thing. So we can see that left hand side is equal to right hand side. Why? This will get cancelled. So I have left hand side is equal to right hand side. So yes, the by parts is being proved by that also. Initially we proved in a reverse thinking way. First way, what we did, we just thought of a product rule, and then we just did the reverse thinking, and then we derived to the result of by parts. And the other way is we have just verified it. We have just verified it. Yes, the result is fine. Why? By just differentiating the left hand side and right hand side and getting the same answer. It means that, okay, fine, the equation holds true, right? Done? Now, the trade which we have to do is between u, which one to be taken as u and which one to be taken as dv, right? And we can only do the trade provided we can easily integrate v du, है ना? तभी ना कर पाएंगे. What was the result? That u dv का integration is equal to uv minus v u dv का integration was, okay, v into, just a sec. This was the result, right? U prime into integration of dv. Okay, this was the result, right? U dv, and we have to do the, okay, it was a function of x, right? So uv, we have to see this way, right? This was the result. Okay, now the trade which we were doing between u dv and v du, how to integrate u dv and v du. we had a trade between these two. I have u dv, another thing is v du. If it is easy to integrate, then I can find u du. If it is not easy to integrate, probably I have to find which one is easy to integrate, right? So the challenging part is which one to be taken as u and which one to be taken as v. Okay, which one to be taken as dv basically. So now the first thing, we won't develop any rule for right now. We'll just believe in a gut feeling, and then after seeing some certain pattern, we'll come to the conclusion, okay, that this is the way we are going to select our u, this is the way we are going to select v, right? So let's start with first function, first problem. What is the problem? X log x dx, right? Now which one to be selected as u and which ones to be selected as v? Now since we have to break things, I want my second function, I want something which can be easily integrated. I want my second function to be something which can be easily integrated. One can be easily integrated? X can easily be integrated. So I'm going to say that, okay, fine, log x into x dx, right? Minus, I'm going to differentiate the log x part. What will be the differentiation of log x? And what is the integration of x dx? Okay. Clear? So what will be the final answer? X square by 2 log x minus x square by 4 plus c. Why we were able to find the answer? Because see, x log x was difficult to integrate, but 1 by x into x square by 2 was easy to integrate. So what was my u? What became my u? This became my u, right? And x dx became my dv, right? Similarly, we discuss, okay, fine. So this becomes my u, this becomes my v, this becomes my u prime, this becomes my integration of v, integration of dv, that becomes v. Agree? Fine. So first thing we found that, okay, the function which is easily to integrate can be taken as the second function, which can easily be integrated, that can be taken as the dv part, right? So let's go to the second example. X e to the power x dx, right? Now since we know that e to the power x has always been easy to integrate, so I'm going to take again ex to be the second part, right? And x as a first part. So I'm going to say x e to the power x dx minus x, what is the differentiation of x? 1 right? This is the way we are going to do it. So it will be x e to the power x minus e to the power x dx, which finally gives me, right? Clear? So we have got another thing, okay, fine. The thing which can easily be integrated should be taken as a second part, and the thing which is difficult to integrate comparatively, we'll take it as a first part. So similarly, this third example deals with x square ex, x square ex dx, right? So which is easy to integrate? Again, e to the power x is easy to integrate, and which is so we can say x square ex minus integration of ex is ex, and what is the differentiation of x square? 2x, and what is the integration of ex? Ex. Clear? Now it's again little difficult to integrate, right? It's again little difficult to integrate, so we are going to further put the thing parts. So things will be x square e to the power x minus, I'm going to take a part again. So again, it will become my second part. So 2x into e to the power x minus, what is the differentiation of 2x? 2. So final answer would be plus. Understood? Clear? So even when we get something difficult, we can further put parts. We don't have to be disappointed कि oh, we are not able to find it in one step. No issue. We can go to the further steps. Now, since we have it has always been easy to differentiate an inverse function, but integrating is a little difficult. We haven't integrated it yet, right? So for the first time, we are going to integrate an inverse function, that is sine inverse x. Let's see how to integrate this. What is the differentiation of sine inverse x? 1 by under root 1 minus x square, right? But we have never yet find any function whose differentiation is sine inverse x. We have to find the anti-differentiation of sine inverse x. So when I see sine inverse x dx, I don't see any other function. I see sine inverse x alone. But I know one. Number 1 is always being multiplied. Right? So 1 is hidden there. So I can consider my other function to be a constant 1. And a constant function is easily integrable, right? So we can say that my sine inverse x is the first part into 1 dx, right? Minus, what is the differentiation of sine inverse x? 1 upon under root 1 minus x square. And what is the integration of dx? Right. So we can say that this is x sine inverse x minus, how to solve this question? We have done last time. My 1 minus x square becomes t. So minus 2x dx becomes my dt. So I'm going to put plus half, and this will become minus 2x dx upon under root 1 minus x square. So finally my answer would be x sine inverse x plus half. This is dt and this is under root t. What is dt into t to the power minus half? Minus half plus 1 is half. Right? This would be the answer. Half and half would be cancelled. So answer would be x sine inverse x plus under root 1 minus x square. Clear? Good. So whenever you see inverse function, you know how to deal with it now. Right? Inverse function, it is difficult to integrate. Right? So you will always consider, whenever you see inverse function, you will think that, okay, fine, I have to keep it as a first part. You all must have heard of eyelet rule, but that is a rule which we apply in most cases, but not in all the cases, right? So we are not going to say eyelet rule, because first, whenever we are going to see inverse, I'm going to put as 1. Whenever I'm going to see log, this is the order. Whenever we are confused, we can put that order. But the idea is we should be able to identify which is easily integrable and which is difficult to integrate, and then we are going to trade it, right? So the trade is always between udv and vdu. If udv is difficult to integrate, I have to see whether vdu is easy to integrate or not. If vdu is easily integrable, my selection is good. Let's say x dx upon 1 minus cos x. Now here is the issue. Which one to be taken as first part and which one to be taken as second part? Now I see x is also easily integrable, and I see 1 upon 1 minus cos x is also easily integrable. But I see x is easily differentiable. I see x is easily differentiable. It is right. So I can easily integrate both of them, but x can easily be wiped out. X can easily be wiped out. So similarly, so I'm going to take x as my first part, and so x minus dx upon 1 minus cos x, sorry, x into dx minus 1x minus x is x gone, integration dx upon 1 minus cos x dx. Right? This is the whole thing which we have to do. Now what is 1 minus cos x? 2 sine square. And what that becomes? The sine square thing will go up. It will become cosec square x. And it's easy to integrate cosec square x. What is it? So I'm going to put x into cosec square x by 2 dx by 2, that is half dx, right? This is the way. So cosec square t dt, this is nothing but cosec square t dt, है ना? So it will become minus x cot x by 2. Clear? Understood? Half यहाँ पे handle कैसे हो रहा है? Now minus cot x by 2 dx, right? So thing will become minus x cot x by 2 plus cot x by 2 dx. एक correction भी करना होगा ना? If I say cot x by 2 dx, I have to put a correction of putting half and then 2 here. Right? Now I can do cot t dt. What is cot t dt? Log plus 2 ln sine x by 2 plus c. Clear? Easy? Done? Okay. So now the next question is very easy now. Sixth part has become easier now. We have already done x 1 minus cos x, and the second part is sin x upon 1 minus cos x. Sum of a integration. Integration of a sum is sum of integration, right? So sixth question is nothing but this plus I'm going to put 1 minus cos x as t. So this will become dt. So this will become log 1 minus cos x. So this plus log 1 minus cos x will be my sixth answer. Clear or not clear? So you see the question, even if it would have come in the examination, it would have given sixth question, not the fifth question, right? Fifth question, and then you have to split sixth question in two parts. Fifth part plus this part, right? Clear? Good. नहीं तो अगर if you would have seen it together, फिर बहुत ज़्यादा confusion होता which one to be taken as first part and which one to be taken as second part. You have x plus sin x in the above thing and 1 minus cos x in a below thing. So whenever you see this type of confusion, split it. If you can easily split it, remember the first rule of integration, that sum integration of a sum is sum of an integration, right? Now show without differentiating. Now remember we talked about islet, and we thought exponential was always in the end, so it will always be taken as second part. But I said that eyelet is not a thing which can be applied every time. It's not a universal law. Eyelet is taken according to our convenience. Now, when I have to prove this question, e to the power x into fx plus f prime x, I'm going to take e to the power x as first function. Sorry, fx to be taken as first function and e to the power x to be taken as second function. So let's say I have to prove it. E to the power x fx plus f prime x. The first law says, first rule I'm going to apply. Right? I'm going to take fx as my first part. Right? So it will be fx into e to the power x minus f prime x e to the power x dx plus f prime x e to the power x dx. So I'm left with e to the power x fx. So whenever you see something like e to the power x into some function plus its derivative, the answer would be e to the power x into that function. Okay, you see? Show without differentiating. We have already proved it. Clear or not clear? So whenever you see e to the power x, if any of this form, e to the power x into fx plus f prime x, the answer would be e to the power x into fx. So whenever you see any type of, whenever you see these type of question, the challenging part is to recognize fx and f prime x and to split them together. Split it, right? Because they will be seeing examples jahan pe they will be integrated together. So we have to split it very carefully. And the moment we will be able to recognize, okay, this is my fx, this is my f prime x, the answer is ex into fx. So the challenging part, whenever we see spot this type of question, the challenging part is to identify fx and f prime x, right? Let's go to question number 8, derive and remember. Last time we remembered 7 identities, right? What was that? 7 integration rules we remembered last time. We derived and remembered it. What was that? Dx upon quadratic and then dx upon under root quadratic. Now the thing is under root quadratic into dx. Now since we know by parts, we can easily differentiate this thing. How to go for it? Let's say my I is under root x square plus a square into dx. Right? This is my I. I'm going to, as we can see, it is very difficult to integrate. Right? I'm going to take this as my first part and 1 as my second part. So it will be x into under root x square plus a square. Integration of dx is x minus integration of dx is x. What is the differentiation of under root x square plus a square? 2 into under root x square into yahi hoga. Now I'm going to cut this. So my thing will be x into under root x square plus a square minus x square upon under root x square plus a square dx. Right? I can write this as plus a square minus a square. Clear? So I can say that x into under root x square plus a square minus under root x square plus a square plus a square upon under root. Right? I know how to, this is already my answer. This is already I have got in a expression form. This I can easily integrate. This one, is it the same question? I. So I'm going to put I on a left hand side. So it will become 2i is equal to this plus this. So I'm going to say that x into under root x square plus a square. What was the formula which we derived? भूल गए? कोई बात नहीं. I'm going to put a square out and I'm going to take a out and I'm going to say dx upon under root x square by a square plus 1. I'm going to take 1 by a here. So I can see this is nothing but dt upon under root 1 plus t square. Whenever we see 1 plus t square, what we take as t? Tan theta. So it will become sec square theta और उसका अंडर रूट sec theta और ऊपर क्या आ जाएगा sec square theta. Sec square theta और sec theta कटेगा क्या बनेगा sec theta. That is log sec theta plus. So this will be something like x into x square plus a square ln sec theta or tan theta. Sec theta plus tan theta, and my tan theta is x by a. So log x by a plus under root 1 plus x square by a square plus c. So finally 2i will be equal to x into under root x square plus a square ln x plus x square plus a square plus constant. Minus log a will go out. Minus log a will be a constant, right? So I can say my 2i is x square plus a square plus ln x plus. So what will my answer? Right? Easy to derive, not difficult. So you have to derive this and keep it in mind. You have to remember it, right? Otherwise it is going to take your time in examination. So if you remember the result, you can directly apply this formula. Now see the ninth question. It is cos x by x minus log x sin x dx. How to deal with this question? By x minus, I can write log x to the power sin x as sin x log x. This is the question, right? What is the differentiation of log x? And what is the differentiation of cos x? So ये कौन सा रूल है? इसका डिफरेंशिएशन यहां है और इसका डिफरेंशिएशन यहां है. Product rule. Remember the product rule. First into the derivative. Product rule दिख रहा है ना? Even if you are not able to recognize the product rule, I can split this integration into cos x by x minus sin x log x dx. Right? I can split it. Those who have already seen it, that it is nothing but a product rule, you can directly apply it as duv, and duv is uv. Now what is u here? Cos x. And what is v here? Log x. Understood? I'm going to put by parts in this part, this first function. So I know dx by x is easily integrable. I know dx by x is, so I'm going to write cos x log x minus, what is the differentiation of cos x? Minus sin x. See, those who have already, the moment they saw the question and they identified it, that okay, fine, it is nothing but a product rule. How we recognize that it is a product rule? We saw the differentiation of this is here and the differentiation of this is here. So I have got something like u v prime plus v u prime. right? It is nothing but a product rule. You must be getting confused a little with the minus thing. Minus is nothing but a differentiation of cos x, right? So those, if you would have recognized in the examination, you would hardly take 15 seconds to answer it, right? And those who won't be able to recognize will go traditional way and will take some time. Clear? Now see the 10th part. It's a very easy question. You can easily see it. Which form it is? Fx plus f prime x. What is the answer of whenever you see this? I don't have to show it. It's very easy to guess because we have already derived e to the power x fx plus f prime x, right? Done. So you don't have to apply by parts here. You can directly put the result. Now 11th, again we have to derive and remember. Okay, do we really have to derive it? X square plus a square, and then we have x square minus a square. So whenever we see a square, I'm going to just put minus a square. Done. So I don't have to. So you can handle that? You can derive it? Or should I show you? Okay, let's show it. X square minus a square dx is equal to x square minus a square minus 2x square by 2 x square minus a square dx, right? So this gone, minus a square plus a square. So 2i is equal to x under root x square minus a square minus a square right? Now again, I'm going to divide it. So it will be 1 by a and it will be x square by a square. So I'm going to put now as sec. So it will be sec square theta minus 1, that is tan theta. And the above we will get sec theta into tan theta. So finally it will be sec theta d theta. So it will be sec theta tan theta upon sec theta tan theta upon sec theta. Just a sec. Sec theta tan theta upon tan theta, right? So sec theta, that will be ln sec theta is x by a plus tan theta is. So finally it will be right. Same, जहाँ पे plus a square था, we just replaced it by minus a square. So you can remember that way. Now see the 12th part. Again, we know how to derive it. We'll say I is equal to under root a square minus x square x, right? Minus x into 2 by under root a square minus a square into minus 2x into dx, right? Now this gone, so it will be x under root a square minus x square minus x square upon under root a square minus x square dx, right? I'm going to put a square and minus a square, right? So I can say x under root a square minus x square minus I plus a square into dx upon, right? So I'm going to write 2i is equal to I'm going to say a square 1 by a dx upon 1 minus x square by a square. So dt upon 1 minus dt upon under root 1 minus t square. What is that? Sine inverse t. So it will be x sine inverse x by a. So final answer would be clear. Done. So basically, whenever you see this type of form, you can easily handle it. Dx upon quadratic, dx upon under root quadratic, dx upon under root quadratic. Right? You can easily handle these three types. और एक और क्या था? Dx upon x into, you can handle this also. We derived it last time, right? How to derive this thing? Simple, same way, x square by a square minus 1. This will be 1 by a. Right? Now I can say this. I am going to take x by a as sec theta, sec theta. This is basically t. So I'll say dt upon at into under root t square minus 1. So I'm going to say, if my t is sec theta, it will be sec theta tan theta d theta upon my at is nothing but sec theta. And what is under root t square minus 1? Basically it is theta. And what is theta? Sec square x by a. Okay, clear? Not clear? So whenever you forget the formula, you forget the result, you can easily find it. It is hardly, it will take 30 seconds or a minute, because you don't have to find all, look at all the steps. You just have to do it little fast. That's it. और जब अगर आप लोग घर पे, if you have already practiced 3 times, 4 times, it will be internalized. And even when during the examination, if you get little paranoid, oh, I think I am not remembering the right answer, you can derive it in 15 seconds, right? See now, x sine inverse x dx. It is very easy for me now. Why? Whenever I see inverse function, I'm not in a mood to integrate it. I'm always in a mood to differentiate it. So I'll say sine inverse x into x square by 2 minus x square by 2 into 1 upon under root. How to solve this question? How to solve this part? X square sine inverse x by 2 minus, or I would say plus, minus x square 1 minus 1, right? Or I can use trigonometry. I can directly apply the substitution. I can directly apply the substitution. How to apply the substitution part? I'm going to take x as sine theta. So this will become sine square theta. I have taken x as sine theta. So my x square becomes sine square theta and dx becomes cos theta d theta upon 2 into cos theta. So this is gone. X sine inverse x by 2 minus half. I'm sure you know how to integrate this. 1 minus cos 2 theta by 2. So I'm going to say x sine inverse x by 2 minus theta by 4 plus 1 by 4 sine 2 theta by 2. Now I can put 2 sine theta. Sine theta was x, cos theta was, and I can put this as 1 by 4. Right? There are various ways you can solve the questions, but you're mathematically should not go wrong, and always try to find the shorter way. Even if you are not able to find the shorter way, go the traditional way, right? You should not commit mistake. Now, how to go for sec cube dx? I see a function sec cube, and then I don't see any other function. But in sec cube, I see two functions. One is very easily integrable, sec square x. So I can break that into sec square x into sec x. And which one should be taken first part? First part should be the one which is difficult to integrate. So I'm going to write sec cube x as nothing but, so I'm going to say sec x into sec minus integration. What is the integration of sec square dx? Tan x. And what is the differentiation of sec x? Right? Now, minus, now how to handle tan square x? Sec square x minus 1. So I'm going to write this as sec x tan x minus I plus, I can easily handle this. So 2I becomes this. So I become sec x tan x plus ln sec x plus tan x. यही होता है ना sec x का, upon 2 upon 2. Clear? Done? Now see question number 15. Again, we are getting something like e to the power x into something. What is that? Sum of two functions. So what is the challenging part? To identify fx and f prime x. So let's see. Whenever I see sine 2x and it is being added to something, I'm not comfortable with 2x. I'm more comfortable with x. So I'm going to reduce things. So e to the power x. So 1 plus cos 2x is nothing but 2 cos square x. That is already 2x. So we'll say 2 cos square x. So 2 cos square x. So 2 upon 2 cos square x will become, oh, I got something. I got something which can easily be integrated, right? Plus 2 sine x cos x upon cos square x. 2 cos square x. So what we got? So what will be the answer? See, easy now? Okay. Now see the next part. X ex to the power 1 upon 1 plus x square. So I see that it's nothing but e to the power x into x upon 1 plus x square. Right? I can do little cooking up with this. Right? I can do I can do +1 -1. So what will I get? Right? Are they related? How they are related? Fx plus f prime x. So what is fx? So what will be the answer? Yes. This one. Module. It was there. Okay, okay, ask. Ex square. Tan minus x into okay integration. Now I see the integration of tan 1 by x is sec square 1 by x plus into कुछ और भी होना चाहिए ना. 1 by x का डिफरेंशिएशन क्या होता है? minus 1 by x square. So I am going to say that I have to integrate this, right? So I am going to say that 3 tan x, 3x square, if I take part, 6x. Okay. I'm going to work on this. So I'll say this as first part and this as okay. So it will turn out to be I'll take this as tan 1 by x and this will be x cube, right? Minus x cube. What is this? Into minus 1 by x square minus x. I think now you can handle. Right? Done? This is the question. Easy? Now you can do it? Okay. My part say, the only thing which triggered me is tan 1 by x and sec 1 by x. Then these were actually helping me out. I just had to figure out how. And that is how we were able to solve it. Okay? Should we go to this next question? Integration is all about following the method, thinking intuitively, right? Now, if you see 17th, we have done 16, right? If you see 17th, now it is little difficult. This question is little difficult. X square plus x plus 1 the whole square dx. I have see some quadratic expression above, some quadratic expression below, and now I have to break it, right? The only good thing is that x plus 1 ka square. And whenever we see x plus 1 ka square in a denominator, we always think of something upon x plus 1. So if we get something upon x plus 1, things will be fine with us, right? So I'm going to see this way as e to the power x into, no, I'm not going to do that. I want x plus 1 in the down and a linear term on the up. See, I'm going to play with a linear upon linear thing. So I see x plus 1 ka square and I know x square minus 1 has x plus 1 as a factor. So I'm going to put that as x square minus 1 plus 2 upon. See, if you get the idea of 2x, do it and see whether you are getting it or not. If you're not getting, come back fast. Don't get into there and start differentiating and finding. See, यहाँ पे दो रास्ते खुल के आ रहे हैं. 2x भी दिख रहा है और प्लस माइनस 1 भी है. अगर 2x पहले तुम्हारे दिमाग में हिट करता है, if it hits first time, go for it. But don't stick to it. Just see that we are getting the path or not. If you're not getting, come back. Okay. See, if I would have done x, तो ये completely constant हो जाता ना, फिर फायदा क्या होता? Right? Now it will become x minus 1 upon x plus 1 plus 2 into, is there any relation? What is the relation? This is fx and this is f prime x, right? The quotient rule, this will be the squared up thing into x plus 1 into the differentiation of the numerator, that is 1, minus the differentiation of denominator into numerator. यही होता है ना product quotient rule. Quotient rule is nothing but a product rule only. Cool? Okay. So now, so 17th is done. So whenever you see ex into fx plus f prime x, you have to do little cooking up. Don't worry about it. दो तीन रास्ते दिखेंगे, but you have to choose the best path. Now let's go for 18. I'm not comfortable with log. I always want to substitute it, right? And there are two log x plus 1 by log x. I can see that log x could मैं differentiate करूँगा, तो I'll get 1 by log x along with 1 by x2, and that is missing, right? So I'm going to substitute log x as my t. When I substitute log x as my t, what will become my x? X becomes e to the power t, and t becomes so now I got something very easy thing, e to the power t into log t plus 1 by t into dt. Easy. So it will be e to the power t log t plus c. So e to the power log x. E to the power t is nothing but x only. E to the power log x is x, and log t becomes log of done. Now the next part, 19, 20, 21, 22, 23, they all are very important and they are somehow same questions. We'll see how. 19th is sine of log x, right? Sine of log x plus cos of log x into dx, right? Sum of integration of a sum is sum of integration. So I can say sine log x dx plus cos log x dx, right? Any problem? No? Now, I am going to take a part of the first function. This first integration I am going to solve it using by parts. So what I am going to do, I am going to take sine log x as my first part. Right? And what will be the integration of dx? X minus, I'm going to differentiate sine log x. It will turn out to be cos by x. And what is the integration of dx? So we got the answer. We got the answer. What will be the answer? This one, plus c. Right? Now, the 20th part, how to solve 20th part. 19th part, I have already given you this thing to cancel it out. But in 20th part, it is not being cancelled out. So we have to further by parts. We have to further by part it. Let's see how. We got sine log x dx as x sine log x minus cos log x dx, right? So how to go for it? X sine log x minus cos log x, x plus minus sine log x by x. So I got minus I. So it will go turn out to be 2I is equal to x minus x. So I will be clear or not clear? Done? Okay. Achha, if you would have solved this question by substitution, I would have taken log x as t, then thing would have become sine t, and dx would have become e to the power t dt. So it would have become e to the power t into sine t. You see this? Same question. Now, whenever you see this type of form, how to go for it? I'll show you. I'll again take by part, and I know sine 3x after differentiating gives me cos 3x, and cos 3x further differentiated gives me sine 3x. So ये recursive sort of कुछ हो रहा है. I again being I is reproduced, है ना? So I'm going to say this as I is equal to sine 3x into e to the power 2x minus 3 cos 3x by 2 भी होगा, right? By 2 cos 3x 3 into e to the power 2x by 2 dx, right? So I'm going to say this as e to the power x 2 sine 3x minus 3 by 2. Further, I'm going to integrate e to the power 2x into cos 3x dx. So I'm going to take cos 3x into e to the power 2x by 2 minus 3 sine 3x minus minus plus into e to the power 2x by 2 dx. So we got the I again, na? This is where we started with I. So we got something like I is equal to e to the power x by 2 sine 3x minus 3 by 4 e to the power 2x cos 3x minus 9 by 4i, right? So I can say 13 by 4i. I can say this. So my I becomes 1 by 13 into 2e2x sine 3x minus 3e2x cos 3x. I got something like 1 upon 2 square plus 3 square into 2, same thing, minus 3, same thing. You saw the relation? I got e to the power 2x, 2 was here, I got here 2 square, and 3x was here 3, I got 3 square here. So you see the next question? You have to show that e to the power x sine bx is equal to ex bahar upon a square plus b square into a sine bx minus b cos bx. The same thing, right? So you understood? 21st, 22nd, whenever you see, if you can remember this in your mind, if you are not able to remember it, it's fine. You can easily derive it, right? So you can easily show this thing because this is a very common question. This is a very common types which appear in the examination, right? So if you remember it, you will take hardly 5 to 10 seconds to answer it. If you are not able to remember it, you will take 40 seconds or a minute. Okay. So you should remember this also, that Ex sine Bx is equal to, it's a very famous type. You will be, must be having questions in your module regarding this format. Okay. So you should, we have already handled 20-second, right? Anna? So whenever you see e to the power x sine Bx, so answer would be e to the power x upon the sum of x के साथ e के साथ जो है a square plus b square into sin Bx will have the coefficient of exponent and cos Bx will have a coefficient of sine minus. Okay. So 23rd can easily be dealt e to the power sine inverse x dx. So I'm going to take sine inverse x as theta. So I'm going to take sine inverse x as theta. So x becomes, so you know how what the question has become, e to the power theta cos theta. You can handle it, right? Now 24th, very easy question. This is nothing but under root x plus 1 ka whole square plus 2 square. I don't have to solve this question. You can solve it with under root x square plus a square dx, right? Good. Next slide. Scan 5. Scan 5. Yeah, you can ask me the question. Okay, what is the question? Root cos 2x upon sin x. I can make this as 1 minus sin square x upon x. T squared minus 1 upon under root 1 minus t squared dt. minus 1 by t minus 1 by t upon 1 minus t square minus 2t square minus 1. 2t square minus 1 square b. Okay. It will be 2t square minus 1 upon 1 minus t square and 2t square minus 1 dt. So now I can put t square as quadratic into quadratic. So I can make this as minus 2t square minus 2 plus 1 upon 1 minus t square under root 2t square minus 1 dt. Okay, fine. So I can make it this as 2 dt upon under root 2t square plus dt into quadratic into under root quadratic. Yeah. Where was the question coming from? So see, the question was, question came from online, and whoever is watching, we can see that. The question was under root cos 2x upon sine square x into sin x dx. So finally what we did, I just made it this as sine square x and made it this as sin x dx, right? So I just manipulated it with minus sin x dx and put minus out. So I put the substitution of cos x as t. So I did that 2t square minus 1 upon under root 1 upon 1 minus 2t square dt, right? Now I removed this part by multiplying it with this. So I got quadratic upon quadratic into this quadratic. And then I got rid of this quadratic by this way. So I got something like 2 into dt upon root quadratic plus dt upon quadratic into under root quadratic. So this type, we are going to handle in the next sheet, how to handle dx upon quadratic into root quadratic. Whenever you see quadratic into under root quadratic, you always do the substitution of x is equal to 1 by t. Whenever you see quadratic dx upon quadratic into under root quadratic, you always substitute it by x is equal to 1 by t. Then the final thing is easy to handle. So we'll be handling this in the next slide, but you can easily handle this. So everybody got the solution, right? I just what did? I made this as under root quadratic upon quadratic, and then finally squared it up, and I got under root quadratic here, and then I manipulated it by getting out this part, and then I got something like this plus this. So I'm going to handle this in the next slide. This type we haven't dealt yet. How to handle dt upon quadratic into under root quadratic. So in next question it will be okay. Okay, then also it will be fine. You will get the same thing. Integration finally will come to the same thing. It's just the thinking, right? So you will get something like cos 2x upon under root cos 2x. Again, the quadratic thing will come. Quadratic into quadratic. Finally, you will arrive to this position only, right? Question 16, part 1. Okay, we are just into. Okay, now I see x squared dx upon x minus 1 into 2x plus 3. What I see is a quadratic expression up and quadratic expression down. So I can easily divide it. So first I'll divide it. What is the product of x minus 1? It will turn out to be 2x square plus x minus 3, right? This is the product of denominator. If I divide x square, I'll just have to multiply by x square half. So it will be x square plus x by 2 minus 3 by 2. So I can write my above expression as half into x minus 1 into 2x plus 3 plus x by 2 minus 3 by 2. Half into this. When I multiply this, I got extra term of x by 2 minus 3 by 2, which I need to subtract. Right? Understood what we did? We saw a 2-degree polynomial up, saw a 2-degree polynomial down. So we can easily divide and get a constant. So we got a constant half minus the remainder portion. The above thing is nothing but x square now. So we can easily break this as dx half minus x by 2 minus 3 by 2 upon x minus 1 into 2x plus 3 dx, right? And I'm going to put half outside. So now we are actually going into the partial fraction form. So first time, whenever we get any something like ax plus b upon x minus alpha into x minus beta, whenever we get something like linear upon quadratic, we try to write this part, the integrand part, the thing which we have to integrate as a partial fraction. So I'm going to say that ax plus b upon x minus alpha into x minus beta can be written as p by x minus alpha plus q by x minus beta. Right? Now the challenging part is, what is p and what is q? How to find p and q? I'm just simply going to say that ax plus b is equal to p into x minus beta plus q into x minus alpha. For finding p, I'll put x as alpha. So it will become a alpha plus b is equal to p into alpha minus beta. I got my p. Similarly, I got my q. And my answer became p ln x minus alpha plus q ln x minus beta. This is partial fraction. Understood? What is partial fraction? We have to observe an integrand. If I see a polynomial function in the denominator and I see a polynomial function in the numerator, if the degree of numerator is higher than the degree of denominator, we are going to divide it. We are going to divide it and find the quotient. Quotient will definitely, depend on the by how much higher my numerator is. If it is of the same degree, the quotient will be constant. If it is cubic, it will be linear or constant. You know that remainder हमेशा उसके degree के नीचे रहेगा. And then whatever you get is, if you have a quadratic expression below, so you will get linear upon quadratic. So I can break this fraction into sum of two partial fractions. And now it is easy to integrate now, right? We'll put the integration of sum is sum of integration, right? So what we did in question 16 part 1, scan 5, yeah, maths 15, this one, scan 5. So in 16 the question was, 16 part 1 question was that we got a quadratic expression up and a quadratic expression down, so we divided it partially to get the answer, right? Everybody understood partial fraction? So we'll see varieties also, or how to deal when we don't get linear. We'll see. Next question, what do you see? That x minus 1. You see the question number 2? We have a linear thing up and a cubic thing down, and although the cubic thing has been factorized, so I can say my fraction x minus 1 upon 2x plus 1 into x minus 2 into x minus 3 is nothing but a by I can see this. I can say this. Now, since I know, I can easily integrate now. It will be a into log 2x minus 1, a by 2 obviously, plus b log x ln and c ln x minus 3. We have already arrived answer, but we haven't yet found what are my a, b, c. So it's very necessary to find a, b, c. They will be the constant. So how to find? We have already discussed x minus 1 is equal to a into x minus 2 into x minus 3 plus b into x minus 3 into 2x plus 1 plus c into 2x plus 1 into, if I put x is equal to 2, I get b. If I put x is equal to 3, I get c. If I put x is equal to minus half, I get a. Acha, why I am putting x is equal to 2, x is equal to 3? To get rid of other constants. Right? Clear? Now similarly, see the question number 3 thing. Cos theta plus 1 into sin theta upon cos theta minus 1 का स्क्वायर. तो क्या दिख रहा है? पूरा फंक्शन cos में है and we have only sin theta out. We have sin theta out. So I can easily substitute it. So I will write this as minus y plus 1 dy upon y minus 1 square into y minus 3. Now since अभी हम लोग जब भी देख रहे थे linear term was not repeating. Now down we have a repeated. So how to handle this whenever you see this? So I'm going to divide this y upon y minus 1 ka square into y minus 3 as a by y minus 1 b by y minus 1 ka square. Why? Tell me, it's just a simple mathematics which you have been doing right from class 8, 9th. It's no new concept. Remember, whenever you had to add something of this type, what you used to do? This is the way you used to do, and the denominator used to be this. Right? So it is nothing new. So when you see repetition of factors in the down, you will always take care by this way. Okay? Clear? So now, how to handle this? Y plus 1 is equal to a into y minus 1 into y minus 3 plus b into y minus 3 plus c into y minus 1 ka square. Right? Now, if I put y is equal to 1, what I'll get? B. If I put y is equal to 1, I'll get B. If I put y is equal to 3, I'll get C. And then I can easily find A. Clear? So I can easily get the answer. I can easily say A log y minus 1, C log y minus 3, and this one will be, it will be a polynomial x to the power n dx form. So you can handle this, right? Now let's say question number 4. Since we have been seeing the question in which we were getting my denominator easily factorizable, right? हमेशा easily factorizable नहीं होगा. Sometimes it will be not be easy to it will be impossible to factorize. Let's see the next example. I got something like dx upon x cube plus 1. So I can break this x cube plus 1 as x plus 1. So I got a linear term and a quadratic term, right? And this quadratic term cannot be further factorized. Why? The discriminant is 1 minus 4, that is minus 3, negative. So how to handle this type of a thing? Again, it is not a very big thing. जो आप class 9 test में कर रहे थे, that is the same thing. 1 by x cube plus 1 is nothing but a by x plus 1 plus x square minus x plus 1. Now tell me, what should be here? bx plus c. Why? It's a quadratic thing. You have a cubic thing. Finally, my numerator can go up to quadratic part, right? So I'll put this as bx plus c. Now I can say 1 is equal to a into right. सिंपल x इज इक्वल टू -1 करते ही a आ जाएगा, है ना. a आते ही क्या करेंगे हम, फिर इसको ओपन कर देंगे. When we'll open it, this will become bx square. I don't see any x square term. I bx square ax square, but a plus b should be equal to 0. So whatever we found a, b will be minus of that. Now then I am left with c. It gives me constant c. It gives me constant c, and it gives me constant a. Only two constant, a plus c. So c is also equal to, a plus c is equal to 1. We have already found a. Constant is there, 1. So we can find a, b, c. And the moment we have found, I can handle this. I can integrate this. Can I handle this? Of course I can handle this. L into the this differentiation part and then dx upon quadratic. It will become a lengthy question. Don't worry. Okay. Integration, even if you have done a right selection of substitution, the questions will become little lengthy. You don't have to lose patience in it, right? And don't think that you have taken a wrong path or something. You will come to the answer. You will arrive to the answer if you are not going anywhere wrong. Now see question number 5. X squared x to the power 4 minus 1 dx. Now when I was seeing the linear term and all everything, I was able to handle, but I see again x square upon x to the power 4 minus 1. I see only x to the power even. I see only x to the power even. So I'll try to write x square upon 1 minus x to the, what was the, x to the power 4 minus 1, right? I'm going to say x square as y. I'm not going to substitute it. I'm trying to break it into partial fraction. So I'm going to say x square is y and x to the power 4 naturally will become y square. So my idea is to write y upon y square as a by right. The moment I got my a, I got my b, I can find my answer. Are they easy to integrate? Yes, they are. This is nothing but tan inverse x, and this is nothing but the formula L x minus 1 x plus 1 wala. Okay. Now, so till here partial fraction is done. Now I'll just there's no question in that, but I'll just tell you. Let's say if you get something like a quadratic expression which cannot be factorized, and that is repeating, then how to break it? Bx plus c upon that expression plus dx plus e upon that expression ka square. The same thing what we were doing in the, okay. So whenever you see all the even powers, then also you can break that into partial fraction, right? Now, when you see something like dx upon linear into under root linear, when you see something like dx upon linear into under root linear, you will always remove under root linear by, substitute under root linear by t square to get rid of the root thing. My question was dx upon x plus 1 into under root x plus 2, right? So I'm going to write under root x plus 2 as t square, right? Under root x plus 2 should be substituted as t square. So x plus 2 is t to the power 4, right? So dx is, so I can see this as dx is nothing but 4t cube dt upon t to the power 4 minus 1 into t, right? Sorry. X plus 2 should be substituted as t square. X plus 2 should be substituted as t square, right? So I can say dx as 2t dt. So I can write this as 2t dt upon t square minus 1 into t. So it's a very easy thing now. Hello? 2 into dt upon t square minus 1. So you can easily handle this, right? Clear? So whenever you see linear upon under root linear, I'm going to replace under root linear by t square. Under root linear by t means inside the thing linear should be equal to t square. We don't have much time. We'll be handling better. Come down. When we see x dx into quadratic into under root linear, again we are going to substitute linear as t square. Why? Because the idea is if I'm going to replace my t if I am going to replace my t by t if I am going to replace x minus 1 as t square, I'll get t and I'll get here t dt. That both will be cancelled and this will turn out to be a quadratic expression and this will be a biquadratic expression. So see how to solve this question. Let's say I say x minus 1 as t square. So dx becomes 2t dt, right? So I can say that x is nothing but t square plus 1 into 2t dt upon x minus 1 into x minus 2 को मैं क्या लिख सकता हूं t square into t square minus 1 upon t, right? Now I got something like t square plus 1 dt upon t square into t square minus 1, right? How to solve this question? Partial fraction. How to substitute? Because I see only even powers. So I'm going to divide this as y plus 1 upon y into y minus 1 and then break it into a by y and a by y minus 1. So finally it will be broken into a by t square and b by t square minus 1 and I can handle a by t square and b by t square minus 1. Understood? Similarly, we don't have much time. I'll just talk about it now. So if you see part 3, quadratic into root quadratic, right? This was what we got. Whenever we see quadratic into root quadratic, I'll just show you this question. Like you have dx upon x square plus 1 into under root x square plus 2. See, whenever you see quadratic into under root quadratic, always try to substitute x is equal to 1 by t y. Because this will have a 1 upon t square thing and the differentiation will also have 1 upon t square thing. So that both thing will be cancelled out. See? So I can write my dx as minus 1 by t square dt, right? And I can write this as 1 plus t square by t square into, I can write 1 plus 2t square by t. So this t square cancel. So something I get like t dt upon 1 plus t square into under root 1 plus 2t square. I can handle this. I can put 1 plus 2t square as my x. I can handle that. Right? That will turn out to be x square dx, x dx. So that will be cancel out t dt. Clear? Or not clear? I can handle this now. Good. No, wait. Okay, yes, we can handle because we got t dt up. Even we can make it linear. We have already come to the known thing, right? Now let's say when you see fourth question, when you see dx upon linear into under root quadratic. See, you see linear here and under root here, and in under root you see quadratic. Now, if I put x is equal to 1 by t, things will get little messier with this thing, right? So instead of that, what I'm going to do, I'm going to put x plus 2 as t, as x plus 2 as 1 by t. See, if I can say dx upon x plus 2 into x square plus 6x plus 7, I'm going to write x plus 2 as 1 by t. See, I'll get 1 by t here and I'll get 1 by t from here also. So t will cancel out. Yahan t square cancel out. We will get something like under root. Okay, under root quadratic part. So I can easily handle that. It's no difficult for me to. You understood or not understood? I'll just show you. Dx will becomes minus 1 by t square dt, and x plus 2 will become 1 by t, and this will become 1 by t square plus 6 by t plus 7. Finally, it will become minus 1 by t square dt into 1 by t into some quadratic expression upon t. I can handle this, right? So whenever you see linear into under root quadratic, replace linear by 1 by t. Now question number 5 is very easy to guess. Why? I got x plus 1 to the cube root plus x plus 1, 1 by 2. What is the LCM of 3 and 2? 6. If I put x plus 1 as t to the power 6, things will be familiar. I'll get a 5-degree polynomial in up and a 3-degree polynomial in down. I can handle that. Question number 6. Whenever you see a something like 1 minus t upon 1 plus t form, what do you think of t as? Cos 2 theta. So I can put root x as my cos theta, or sorry, x as cos square theta. I'm going to put x as cos square theta. So I can write dx as 2 sin theta cos theta d theta, whatever with negative plus minus, take care of that. So I get something like 2 sin theta cos theta d theta, and I got something like 1 minus cos theta upon 1 plus cos theta, which finally turned out to be tan x by 2, tan theta by 2. So I got something like, tan theta by 2 and minus 2 sin theta cos theta d theta. ऐसे ही कुछ होगा ना? See, constant पे handle कर लेंगे बाद में. But this is the what. Now I can easily handle this. Why? I can put my sin theta as sin theta by 2 into cos theta by 2. I'm not taking care of constant. You don't worry about that. Okay. Right. So what will this? Cos theta will be gone, and this will become sin square theta by 2. Here you got cos theta. Handle. I can write cos theta as 1 minus, and I can handle sin square theta by 2, and I can handle sin to the power 4 theta by 2. Right? So I can handle this question. This question is lengthier but not difficult. Right? Similarly, if you see question number 7, you see something like under root quadratic upon linear. Sorry, under root linear upon. So it's very easy. I'm just going to substitute x plus 2 as t square. So my thing will become t, and that everything will come out to be very familiar thing. Now similarly, it's far easier than 7, 1, 8. ये नीचे ही आ जाएगा linear, ऊपर चला जाएगा cubic. I can handle this. It will become a polynomial thing. Sin square log x, we have already handled sin log x, and I can already handle sin square log x. How? I'm going to put it as 1 minus cos log x, 1 minus cos 2 log x by 2. 1 minus cos 2 log x by 2, and I can handle cos 2 log x. We have already handled it, right? Question number 10 is easier actually. I see under root quadratic term into a linear term. So I'm going to break my linear term into, I'm going to break x as L into, what will be the derivative of x square plus 2x plus 5? 2x plus 1 plus m. And then I can handle it. Clear? Question number 11, if you see, x to the power 6 tan inverse dx plus I2 is this. We have to find 7I2 plus I2. So if I going to work on I1, I'm going to say I1 will turn out to be, see, this thing is telling me what to take my first term and what to take my second. Inverse है तो हमेशा हम उसे first ही लेंगे. So tan inverse x into x to the power 6, sorry, 7. So you got 7 also, right? Minus x to the power 7, 7. So it will go and it will finally turn out to be the same thing. Next page, please. I can 5 minutes more now. Sixth scan 6 आज ही डाला है scan 6 हाँ वो रहा scan 6 okay I'll just take orally things, right? 18 first I can handle it by substituting x to the power x as t. Things will turn out to be, final answer would be x to the power x. Okay, second part, yeah, this is very important. When you see dx upon under root x minus a into b minus x, see, we already know one method, under root quadratic, right? But things are little messier if you go that way. But I can make it very easy by substituting x as a cos square theta plus b sin square theta. If I substitute this, my dx will become minus 2a sin theta cos theta plus 2b sin theta cos theta. So finally it will be 2 into b minus a sin theta cos theta, right? And my x minus a has also become a very good term. Why? A cos square theta minus a will become minus a sin square theta. So finally it will be b minus a sin square theta. And b minus x has also become a very fine term. It will turn out to be b minus a cos square theta. And they are in under root. b minus a बाहर निकल जाएगा, ये कट जाएगा. Sin theta cos theta सब कट जाएगा, बचेगा 2d theta. So 2 theta. So answer will be 2 theta. Theta को कैसे replace करेंगे? I can say tan square theta is nothing but x minus a by b minus x. So my theta is tan inverse under root this. है ना? Clear? So whenever you see this, you have to deal with this. Similarly, 3, we can handle 3. Partial fraction, we can handle 4th also. Wait a minute, there is anything more important to talk? Oh, there are. So maybe in next class, before the definite integration part, we'll discuss some of the part, because there are few important things which I want to discuss in this miscellaneous thing. So don't worry, but we have actually more or less finished up the indefinite part. Okay. So in next class, we'll first discuss this sheet and then we'll go to definite integration. Okay. Thank you.
Very good afternoon, all of you. Today we are going to start with the next chapter, that is carboxylic acid. This topic will be dealt in two distinct lectures. First half of the topic will be done today, and the following lecture will cover the remaining portion. Okay, so what we are going to concentrate today on is the preparation and the properties of carboxylic acids. All right. This is the outline of the lecture of what we will do today. We will start with the introduction of carboxylic acids. We will learn what carboxylic acids are, what is their structure like, okay, and then we will see their common names. IUPAC nomenclature you have already learned, so you know how to give the IUPAC nomenclature to an organic compound. But for many organic compounds, common names are also equally frequently used. Okay, so it is important that you learn the common names of the commonly occurring organic compounds also. So we will learn some of the common names of the carboxylic acids. Next, we will go on to the general methods of preparation of carboxylic acids. There are 8 distinct methods which are used to prepare carboxylic acids. You will find that some of these methods you have already learned in the previous lectures, and there will be some new methods which we are going to learn today. Okay. Then we will go to the physical properties of carboxylic acids. We will discuss about their solubilities in polar as well as non-polar solvents. We will discuss the trends in their melting point. Okay. Next would be the acidity of carboxylic acids. We will learn what makes carboxylic acids acidic, number 1. We will learn why is it that carboxylic acids are stronger acids than alcohols and phenols. Also, we will learn what is the effect of substituents on the acidity of carboxylic acids. Okay, and in the end, we will take up questions based on what we have discussed today. Okay. So, what are carboxylic acids? If you look at the structure, we have in the last class discussed 2 compounds which have a carbonyl group, that is the aldehydes and the ketones. Carboxylic acids also have a carbonyl group, but in addition to the carbonyl group, they have a hydroxyl group which is attached to the same carbon. Is that okay? So this group is what we call the carboxylic group. Now attached to this carboxylic carbon, you have this R. This R can be an alkyl group. If it is an alkyl group, then those carboxylic acids are aliphatic carboxylic acids. If this R is an aryl group, then they are called aromatic carboxylic acids. Then there are, in naturally occurring carboxylic acids, you find that this R happens to be a long chain of hydrocarbons. If it is a long hydrocarbon chain having C11 to C17 carbons, if you include this carboxylic carbon also in that, that means it becomes C12 to C18 carbon. So all those carboxylic acids, they are found to occur in nature. They are constituents of fats. That is why those carboxylic acids, they are also called fatty acids. Okay. Now, if you see here, the general formula of the carboxylic acid can be written in 2 ways. It is either CN H2N O2, or you can remove the carboxylic group. In that case, the general formula will be Cn H2n plus 1 COH. Is that okay? Now, these are some of the naturally occurring carboxylic acids which are commonly occurring, which we come across. This is the first compound. If you look at this, this is the simplest of carboxylic acids. Yeah, it is the common name is formic acid. This compound is acetic acid. Vinegar we all use in our kitchens. Vinegar is nothing but acetic acid. This compound is benzoic acid. Okay. If you look at this compound, this is 2-hydroxy benzoic acid. This compound is commonly known as salicylic acid. Now, I hope you all heard of aspirin. Aspirin, everybody has heard of? Yeah. Aspirin is an acetyl derivative of salicylic acid. That is 2-acetoxy benzoic acid. That is the systematic name of this compound, aspirin. Okay. Besides that, another compound which you commonly come across, all of us, some point in time we have backaches. Okay. In that case, all of you might have used Move. Your mothers, in case of backache, they have used Move. Iodex also. Chief constituent of all these painkillers is this compound. This compound is called oil of wintergreen. Another systematic name for this is methyl salicylate, which is a methyl ester of salicylic acid. Okay. That smell in iodex is because of this compound, oil of wintergreen. Okay. And this compound is, if you see, methyl group attached to benzene ring is toluene. Okay. So this compound is para-toluic acid. Okay. From toluene, toluic acid. So para-toluic acid. Okay. So these are some of the commonly occurring carboxylic acids, and I have given you some of their applications in our daily life. Right. Let us look at now the structure of the carboxylic acid. This carbon of the carboxyl group is sp2 hybridized. So the bond angle is approximately 120 degrees. It is a planar molecule. Okay. So what happens here is that the 2p orbital on carbon overlaps with the 2p orbital on oxygen to form the pi bond, right? And also the 2p orbital on carbon can overlap with the lone pair orbital on this oxygen of the hydroxyl group. That is why the lone pair of electron on this oxygen can get delocalized. Okay. If you remember, we have done delocalization in the aldehydes and ketones. Now here what happens is that you have a carbonyl group, and this carbonyl group offers a minus I effect because of the electropositivity of this carbon. So what happens here is that these lone pair of electrons on oxygen, they get delocalized. like this. Okay. You can see here how the lone pair has got delocalized, right? So I have shown a formic acid example here. So how the lone pair of electrons have got delocalized. The structure has been shown here. And this structure is only showing the polarization of the carbonyl group because of the electronegativity difference between the carbon and the oxygen, right? Okay. Next, let us come to their common names. Common names of organic compounds are normally derived from the source from where you obtain these organic compounds. Okay. The source determines their names. For example, let us come to this compound, formic acid. The name formic has come from the Latin word formica, which means ants, because it was first obtained from red ants. Okay. Another example is that of acetic acid. I told you it is vinegar, in the food industry used as vinegar. Acetic acid word comes again from a Latin word acetum, okay, which means vinegar. Another example is that of butyric acid. You can see here butyric acid. What is butyric acid? The IUPAC name will be butanoic acid. The word butyric has again come from a Latin word butyrum, which means butter, because rancid butter, if you have observed during moist weather, if you keep the butter outside for 2-3 days, it gets a foul smell. The foul smell is because the butter gets rancid. The ester linkages are hydrolyzed to small chain carboxylic acid, and one of the chief constituents of those is the butyric acid. Okay, that is why the word butyric from the word butyrum, which means butter. Okay, so these are some of the examples to tell you how the common names of the carboxylic acids have come into being. All right. Let us now go on to the different methods of preparation of carboxylic acids. The first method of preparation is from the oxidation of primary alcohols, aldehydes, and alkyl benzenes. If you recollect, in the last class when we were doing aldehydes and ketones, I told you when you do oxidation of primary alcohols with strong oxidizing agents, they are directly converted to carboxylic acids having same number of carbons. So we will see how, we will take one example just to revise and see how primary alcohols are being oxidized. Another reaction of oxidation of aldehydes also we have done in the last class. We have seen how by using either strong oxidizing agents as well as by using weak oxidizing agents, because of the higher reactivity of aldehydes, it is possible to convert them into carboxylic acids having same number of carbons, right? Next reaction we will see for alkyl benzenes, and we will see irrespective of the nature of the chain length. On oxidation, the alkyl benzenes will give you carboxylic group. And the advantage of this reaction is that from the number of carboxylic groups which are attached to the benzene ring, we can predict the number of side chains which are attached to the ring, because each of those side chain on oxidation will give one carboxylic group. Okay, so this is very, very useful when you have to do structure elucidation, when you do those roadmap questions. You know, If you have more than one, if you have two carboxylic group, that means there are two side chains. All right. Okay, the next reaction would be the oxidative cleavage of alkenes and alkynes. This you have done in the hydrocarbon chemistry. We will see how alkenes and alkynes can be oxidized to carboxylic acids having fewer number of carbons. Okay. The next reaction would be the carbonation of Grignard reagent. Grignard reagents can combine with carbon dioxide and can be converted into carboxylic acid. Now, the advantage of this reaction we will learn is that it offers a method of converting alkyl halides or aryl halides to carboxylic acids having one carbon more. That means you can use it as a step-up reaction by increasing the number of carbons by 1. Okay. Next would be the hydrolysis of acid derivatives and nitriles. We will see how acid chlorides, acid anhydride, esters and nitriles can be hydrolyzed in the acidic or alkaline conditions to give carboxylic acids having same number of carbons. Okay. Next is the haloform reaction. Haloform reaction we have done in the last class during the chemistry of aldehydes and ketones. We learned that haloform reaction can convert a methyl ketone to a carboxylic acid having one carbon less, right? The next reaction would be the periodic acid cleavage of the vicinal diols or diketones, 1,2-dicarbonyl compounds. They can be oxidized with periodic acid, where we will learn there will be cleavage across the carbonyl group taking place, giving you carboxylic acids, again having fewer number of carbons. Okay. The next reaction would be the hydrolysis of 1,1,1-trihalides. You will see that those hydrocarbons where you have 3 halogen atoms being attached to the same carbon will be hydrolyzed to carboxylic acids. Okay. And the last of the reactions would be the carbonylation reaction, where we will learn how an alkyl halide can be converted again into carboxylic acid having one carbon more through the formation of alkoxides. Okay. And this reaction hydrocarboxylation is a reaction which is used for stepping up alkenes. If you have an alkene and you want to convert it into carboxylic acid having one carbon more, you can do this hydrocarboxylation reaction, which is commonly known as the Koch reaction. Okay. All right. So let us start with the first reaction, that is the oxidation of alcohols, aldehydes and alkyl benzenes. Now you have learned when we were doing the aldehyde preparations, if you have a primary alcohol and you are doing oxidation with strong oxidizing agents like potassium acidic or alkaline potassium permanganate, you can use potassium dichromate, you can also use nitric acid, you can convert primary alcohols to carboxylic acids via formation of aldehydes. The primary alcohols are first oxidized to aldehydes, which will then be oxidized to carboxylic acids having same number of carbons, right? So this reaction again I have shown here. If you have an aldehyde, we have learned last time you can do oxidation with strong oxidizing agents like acidic alkaline KMnO4. You can use potassium dichromate. Also, you can use mild oxidizing agents like Tollens reagent or Fehling solution in case it is an aliphatic aldehyde. Again, you can oxidize 2 carboxylic acids having same number of carbons. right? Now, what we are going to discuss at length here is the oxidation of alkyl benzenes. Now, what you find is that alkyl benzenes on oxidation with acidic or alkaline KMnO4, potassium dichromate, chromic acid can be oxidized to carboxylic acid. And I told you 5 minutes back that irrespective of the length of the carbon chain, on oxidation, it will be oxidized to only a single carboxylic group, right? What I mean here is, so you have one carboxyl group being generated per alkyl chain, irrespective of the chain length, right? For example, if I have this compound, or I have this compound. What is this compound? This compound is ethyl benzene. Huh? And what compound is this? This compound is isopropyl benzene, right? It is isopropyl benzene. So either of these two compounds, when you oxidize, the product is going to be the same. Both of them on oxidation, either by using any of the oxidizing agents. I have just now told you, you use potassium permanganate in the acidic or alkaline medium, you use potassium dichromate, or you use nitric acid. Will give you only benzoic acid as the product. Okay? Now just elaborating on what I said is, if you have more than one alkyl group attached to benzene ring, then example, this compound, this is 1,4-diethyl benzene, right? If I do oxidation of this with KMnO4 in alkali, the oxidation product will be benzene 1,4-dicarboxylic acid. This compound is commonly known as terephthalic acid. Okay. All right. So I told you that depending upon number of carboxylic groups that you get bound to the benzene ring on oxidation, you can relate it to the number of side chains which are attached to benzene ring, right? One very important thing that you have to remember here, only those alkyl chains which are primary or secondary can be oxidized under these reaction conditions. If you have a tertiary alkyl chain, it cannot be oxidized under these reaction conditions because the primary condition for oxidation to take place under these conditions is the presence of a hydrogen attached to this carbon, alpha carbon. This is the alpha carbon to the ring, right? There has to be one hydrogen attached. If there is no hydrogen attached, those compounds will not give you any oxidation product on oxidation under these conditions. All right? Let us go on to the next reaction. Next is the oxidative cleavage reaction. Now please understand there are two words. Oxidative cleavage means there is oxidation taking place, plus there is also cleavage. There is a breaking of the bond taking place. That is why the word oxidative cleavage reaction. Now these oxidative cleavage reactions can be done for both alkene as well as for alkynes. And in both cases, please remember, you will get carboxylic acids having fewer number of carbons. So you can see on the board here. If you have this compound, what is this compound? This compound is 2-butene, right? And you do the oxidation can be done by potassium permanganate in the acidic or alkaline condition, or by potassium dichromate or chromic acid, right? So what will happen is, you have a cleavage taking place across the carbon-carbon bond. The simple thing that you have to do is that remove that double bond and change each of these carbons which were attached to a double bond to carboxylic group, and you get your product, right? Change each of the carbons, just remove this double bond and change each of these carbons which were linked by a double bond to carboxylic group, and you get your product, right? Now in this case, since my alkene is a symmetrical alkene, the product obtained will be only acetic acid, right? So you have to remember, in case the oxidative cleavage is giving you only a single product, it indicates that you have a symmetrical alkene present. Okay? Next, let us take one example of an alkyne. Now, if you have an alkyne, this is 2-butene, they can be subjected to oxidative cleavage either by ozonolysis reaction or by doing a catalytic oxidation, as we have done in case of alkenes, potassium permanganate or dichromate in acidic or alkaline condition. You can use either of these oxidizing agents. Again, the same rule. Please remove the multiple bond and convert each of these carbons to carboxylic group. Okay? So now please understand, these oxidative cleavage reactions will have synthetic value. Synthetic value means you can use it in the laboratory to prepare carboxylic acids only if you are starting with a symmetrical alkene or a symmetrical alkyne. If your alkene or an alkyne is not symmetrical, in that case, you will get a mixture of product and the reaction will not have any synthetic value, right? For example, if I have one butene and I do the oxidative cleavage reaction here, so what will happen? My product will be methanoic acid and propanoic acid. You will get a mixture of products being obtained, right? Now please see, can you tell me how this ozonolysis reaction takes place for alkyne? How does the reaction proceed? The ozonolysis reaction, if I have an alkyne, how will the reaction take place? You will have this product being formed. right? And then it will give you on hydrolysis dicarbonyl compound. Yeah? And which will be oxidized by hydrogen peroxide, which is generated as a byproduct in this reaction. Right? So you get a 1,2-dicarbonyl compound, which is oxidized by hydrogen peroxide, and you will get cleavage taking place across the carbonyl carbon, forming 2 carboxylic acid molecules. Right? Okay. You can see on the screen, I have taken a general reaction here. You have an alkene here. When you do oxidation with potassium permanganate, cleavage will take place across this carbon-carbon double bond, and you get the corresponding carboxylic acids here. Similarly, if you have an alkyne here, again, if you do ozonolysis or oxidation with potassium permanganate in alkali, there is a cleavage taking place. There is a cleavage taking place across the carbon-carbon triple bond, and you will get carboxylic acids having 2 molecules. Yeah, two molecules of carboxylic acid will be obtained. Okay. Next is the Grignard synthesis. So a Grignard reagent can be used to prepare a variety of organic compounds. It can also be used, we have learned the application of Grignard reagent reactions in the reactions of aldehyde ketones, where we could prepare primary, secondary and tertiary alcohols from aldehyde ketones, right? Now, if you have Grignard reagent, and you react it with carbon dioxide, what will happen? Because the carbon here is electropositive, you have a nucleophilic attack taking place on this electropositive carbon, and it will generate a carboxylate salt. This carboxylate salt on hydrolysis will give you carboxylic acid. So what you see here is that this reaction can be used to convert Grignard reagent to carboxylic acids. Now indirectly, please understand, how do you obtain Grignard reagents? You obtain Grignard reagents from alkyl halides or from aryl halides. So that means this reaction offers a method of stepping up the alkyl or the aryl halides. You can convert the alkyl halides or aryl halides to carboxylic acids having 1 carbon more, right? We will just take few examples. This is the reaction I have depicted here. You can see the nucleophilic R group attacking the electropositive carbon, and this lone pair of electron taking the electropositive magnesium to form the carboxylate salt, and on hydrolysis giving you carboxylic acid, right? Now let us talk about the application that I said for Grignard synthesis. For example, if I have methyl bromide, okay, and if I react it with magnesium in dry ether, that's how you prepare the Grignard reagent. Now please write the product. What product will you get when you react with magnesium? Write the structure of Grignard reagent. And now you react it with carbon dioxide. So what will be the product that you will get here? Yeah. Methyl bromide we have converted into acetic acid, which is a 2-carbon molecule. You're right. Now similarly, you can do the same reaction for aryl halides also, right? Let us go to the next reaction, that is the hydrolysis of the acid derivatives. What are the acid derivatives? You know that acid chlorides, acid anhydrides, esters, these can be hydrolyzed either in the acidic or in the alkaline conditions to give carboxylic acids having same number of carbons. Okay, that is important. Let us write the general reaction. So you will get carboxylic acid. आप लोग गए ट्रांसमिशन में गए ना? आवाज ठीक हो गई है? नहीं अभी ठीक नहीं आवाज. क्यों हो रही है वाइब्रेशन? तार से नहीं होता है. So we were discussing the hydrolysis of the acid derivative in the acidic or the alkaline conditions to give carboxylic acids having the same number of carbons, right? Now, so this is the reaction where Z can be Cl, it can be OR if it is an ester, it can be OCOR if it is an anhydride, and it can be NH2 if it is an amide. Right? Now let us see how the reaction will take place if the reaction medium is alkaline. For example, OH minus will act as a nucleophile and it will attack the electropositive carbon. That is how the reaction will take place, right? So, okay. You can see on the screen, I have shown how the acid derivatives have been converted into carboxylic acids having same number of carbon. Now, the similar reaction can be done for alkyl nitriles also. Nitriles, they can also be hydrolyzed in the acidic or in the alkaline condition, but the reaction here proceeds in 2 steps. Okay? The first step will lead to formation of an amide, and which will further get hydrolyzed and it will give you carboxylic acid. Okay? Let us see how this reaction takes place. Now that we have written general reaction for the acid derivative, you should be able to understand how the reaction will take place. For example, if I have a nitrile and I react it with alkali, and then this will tautomerize very quickly. To form the corresponding amide. In the next step, what will happen? The same kind of reaction. Now for amide, you should be able to understand how the reaction takes place because we have depicted the general mechanism, right? So this on further hydrolysis, alkaline condition use kiya hai here. So the alkaline condition, the product obtained, please understand, if you are using alkaline condition, you will get carboxylic acid salt. Okay, so that has to be hydrolyzed by using dilute acid. You use acidify it by using dilute HCl and you will get carboxylic acid as the product, right? So in the next slide, I have shown one reaction of how alkyl cyanides will give you carboxylic acid. Now again, you can see here in this reaction, the advantage of this reaction. Again, the advantage of this reaction is that this reaction can also be used to convert alkyl halides to carboxylic acids having 1 carbon more, right? To carboxylic acids having 1 carbon more. Now, what is that reaction? Let us write the reaction first. If you have alkyl halide, I have taken here cyclohexyl bromide. When you react with Cn minus, you have a nucleophilic substitution reaction taking place, right? To give you the corresponding nitrile, and then this will be hydrolyzed to give cyclohexane carboxylic acid as the product. Now, one question I have here. We learned that Grignard reagent reaction can be used both for alkyl as well as aryl halides to get carboxylic acids having one carbon more. Now here I have converted an alkyl halide to a carboxylic acid having one carbon more. Is it possible to use the same reaction for aryl halides also? The answer is no. Aryl halides do not undergo nucleophilic substitution reaction. So if I have bromobenzene and I try to react with cyanide ion, there will be no reaction taking place. So please remember, if I have to convert aryl halide to carboxylic acid having one carbon more, I can use the Grignard reagent reaction. I cannot use the nitrile reaction. All right? Okay. Let's go to the next slide. Next is the haloform reaction. Haloform reaction we have done in the last class. If you recollect, it is a reaction for methyl ketones, compounds which have a CH3CO group. Okay, right? These kind of compounds which have a CH3CO group or a secondary alcoholic group like this, they can be subjected to iodoform reaction, and or you can use, instead of using iodine, you can also use bromine or chlorine. The product is a carboxylic acid having one carbon less, right? For example, if I use 2-butanol and I react it with iodine in alkali or sodium hypoiodide, what happens is, I told you, remove this one carbon as iodoform, right? And the remaining will come as the sodium salt of carboxylic acid, right? Correct? So I've shown here how this CH3CHOH group oxidized to carboxylic acid, and again a methyl ketone if you have oxidized to carboxylic acid salt on reaction with halogen in the alkaline condition, right? Okay. The next is the per-iodic acid cleavage. If you have 1,2-diketones or 1,2-dialdehyde, that means you have a carbonyl group residing on the adjacent carbons. These compounds can be oxidized by per-iodic acid. And what will happen? You will have a cleavage taking place across this bond. Okay? And again, you get carboxylic acid having fewer number of carbon. Only cleave this bond, which is linking the two carbonyl groups, and convert them, each of them, into the carboxylic group, right? Another example you can see here. And one more example is here. 3 different types of 1,2-dicarbonyl compounds on cleavage, giving you different types of carboxylic acids as the products, right? Can we go to the next slide? Okay. The next is the hydrolysis of 1,1,1 trihalide. If you have a compound where there are 3 halogens attached to the same carbon, on hydrolysis, they will give you carboxylic acid having same number of carbons. One example I have taken here. Please see, let us see how this reaction is actually taking place. This compound is called benzotrichloride. Okay. When you hydrolyze it, what will happen? Each of these Cl will be replaced by OH. Nothing but a nucleophilic substitution is, right? In the last class also I told you that such compounds are not stable. They will eliminate very quickly a molecule of water. Right? You can see here we have converted benzotrichloride to benzoic acid. Okay? Can we go to the next slide? Okay. The next reaction is the carbonylation reaction. Carbonylation reaction is a reaction of alkoxides. You can use sodium or potassium alkoxide. React it with carbon monoxide and heat it. You will get carboxylic acid having 1 carbon more than this alkyl chain. So immediately you should spot a step-up reaction taking place. How you can prepare sodium alkoxide? Sodium alkoxide we can prepare from alkyl halide. How? You can take alkyl halide, react it with aqueous NaOH. What will you get? You will get alcohol. This alcohol you react then with sodium metal. And you will get the alkoxide. And this alkoxide, when you react with carbon monoxide and you are heating it, you will get sodium salt of carboxylic acid, which on acidification is giving you the carboxylic acid. So what you are seeing here is, again, it offers an indirect method of conversion of alkyl halides to carboxylic acids having 1 carbon more, right? A step-up reaction. The next slide is the hydrocarboxylation reaction of alkenes. Again, it is a step-up reaction. Earlier, we had learned a reaction of alkenes being converted into carboxylic acids where there was a cleavage taking place and you were getting carboxylic acid having fewer number of carbons. Now, this is a reaction by which you can convert alkenes to carboxylic acid having 1 carbon more. So it is a step-up reaction taking place here. You can see. Now how to write the product? It is simple. What you do is you write the alkene. You attach hydrogen to one of the carbon and the carboxyl group to the other carbon. But please remember, in case of an unsymmetrical alkene, the hydrogen will be attached to the carbon which has more number of hydrogens attached to it. Okay, in this case, it's a symmetrical alkene. If I replace this symmetrical alkene by an R here, okay? So what will be the product? Attach hydrogen here and you attach a COOH group on the other carbon and you get your product, right? So the product will be okay. Okay, beta. Let's go to the next slide. So with this, we have finished the different methods to prepare carboxylic acids. Next would be their physical properties. Okay. The first of the physical properties that we'll discuss is the melting point. Now, there are three important trends that you have to remember when you discuss the melting point of carboxylic acids. The first thing is the oscillation effect or the sawtooth effect or the alteration effect that we call. What is that? That is that carboxylic acid having even number of carbons will have melting point higher than the carbon chain having one carbon less or one carbon more. That means if I take a C8 acid, it will have melting point higher than both carboxylic acid having C7 or C9 carbons. Now, what is the reason for this? The reason for this is that in case of an even chain carboxylic acid, the terminal methyl and the carboxyl group, they are facing away from each other. I will show you on the board. If you see here, this is butanoic acid and this is the pentanoic acid, right? The terminal methyl group and the carboxyl group, they are away from one another. And because they are away from one another, these structures, they can fit better in the crystal lattice. Because they fit better in the crystal lattice, there will be stronger intermolecular forces of attraction. And because of the stronger intermolecular forces of attraction, their melting points will be high. Is that okay? So the first thing, even chain carboxylic acid will have melting points higher than those of odd chain carboxylic acid. The second thing is the introduction of a double bond lowers the melting point of the carboxylic acid. There again, in unsaturated carboxylic acids, the cis acids have melting points lower than the trans acids because the cis acids do not again fit well in the crystal lattice. I have written here, you can see. The double bond, especially the cis, have lower the melting point of the carboxylic group. Again, because they're not fitting better in the, they don't fit well in the crystal lattice. Okay. The third very important thing is you find that the melting point of aromatic carboxylic acids are higher than those of aliphatic carboxylic acids. Again, because the benzene ring is planar, it fits better in the crystal lattice. Because it fits better in the crystal lattice, again, stronger intermolecular forces of attraction. Because of stronger intermolecular forces of attraction, higher melting points. Okay, so aromatic acids have higher melting point than the aliphatic acids. Okay. Next, let us talk about the solubility of carboxylic acids. You find that aliphatic carboxylic acids having up to 4 carbons, that is up to butyric acid, they are completely soluble in water. However, as the carbon chain length increases, the solubility goes on decreasing. Now, before we answer why the solubility is decreasing on increasing the chain length, let us first understand what makes carboxylic acid soluble in water. Now, please understand that carboxylic acids are polar. They are more polar than alcohols. They are more polar than aldehyde and ketones. This higher polarity is because of the inductive effect of the carbonyl group, because of which the lone pair of electron get delocalized and the oxygen is acquiring a full negative charge. Okay? Because it has a full negative charge, the negatively charged oxygen can form stronger hydrogen bonds. Now, for any compound to be soluble in water, it should either act as a hydrogen donor or it should act as a hydrogen acceptor or both. Now, carboxylic acid is both a hydrogen donor as well as hydrogen acceptor. Over and above that, you have oxygen carrying a full negative charge, so it can form very strong hydrogen bonds with water. Because of which you find that the lower members of the carboxylic acid family are highly soluble in water. Right? Let us write the hydrogen bonded structure. That's how you can show the hydrogen bonding in carboxylic acids. See, here it is acting as a hydrogen donor and here it is acting as a hydrogen acceptor, right? Forming extensive hydrogen bonds in water. So as the chain length of carboxylic acid will go on increasing, you can see they have a non-polar hydrocarbon part or the hydrophobic hydrocarbon part also present. As the chain length increases, the influence of the hydrophobic part is increasing. That is why the solubility goes on decreasing beyond C4 carbons. In fact, you find benzoic acid is insoluble in cold water. Though it dissolves in hot water, practically insoluble in cold water. Okay? So aromatic carboxylic acids, they have very little solubility in water. But you also find that carboxylic acids, they are soluble in organic solvents like chloroform. They are soluble in alcohol, again because of the formation of dimeric structures. This is a unique property which is characteristic of carboxylic acids, that in aprotic solvents and in solution state, they can exist in the form of dimers. Let us write that dimeric structure. And these dimeric structures are so strong that even when they vaporize, in the vapor phase also they are existing in the dimeric form. Then go to the next slide. The next of the properties is the boiling point. Again, another property of carboxylic acids is the fact, because of their unique structures, they are not volatile as compared to the corresponding alcohols. Because of the polarity, they are extensively hydrogen bonded. I have shown the dimeric structure which exists in the vapor phase and in aprotic solvent, and in solution phase, they are existing as extensively hydrogen bonded structures where the hydrogen bonding takes place through intermolecular hydrogen bonding. You have extensive intermolecular hydrogen bonding taking place in solution phase, which makes them practically non-volatile. Beyond actually C8 carboxylic acids, they are waxy solids and absolutely non-volatile in nature because of the extensive intermolecular hydrogen bonding. I will show the structure, how to depict the intermolecular hydrogen bonding. Like this. Okay. That's the dimeric structure I've already shown you, how the dimerization takes place. So either you can have dimerization taking place, which I told you takes place in the vapor phase or in the aprotic solvent, or you have extensively hydrogen bonded structure like this, which is existing in the solution phase, which is responsible for the non-volatile nature of carboxylic acids and the fact that carboxylic acids, they have high boiling or melting points. Okay. Next, we will come to acidity of carboxylic acids. What I'm going to do here is that I will first try to relate the acidity of alcohols, phenols, and carboxylic acids. We will try to answer what makes carboxylic acid stronger acid than alcohol and phenol. And then we will study the effect of substituents on the acidity of carboxylic acids. Okay, so let us look at these three structures, these three functionalities. Alcohols and phenols you have already studied. If you look at their pKa values, the pKa value for alcohol is about 16. For phenol, it is about 10. Whereas Under normal conditions for carboxylic acids, the pKa value lies between 4 and 5. And I hope you know that there are two different ways to judge the acidity of a compound. You can judge the acidity either by comparing the dissociation constants, the Ka values, or by comparing the pKa values. And you know that the stronger acids, they have higher Ka and lower pKa values, right? So you can see here that the carboxylic acids, they have much lower pKa values as compared to the phenols and alcohols. Now let us try to answer why. What is happening in case of carboxylic acids? The first important point we have been repeating again and again is the inductive effect. Okay, minus I effect of carbonyl, because of which you have resonance. And because of resonance, this oxygen is acquiring a positive charge. And this positively charged oxygen, being a highly electronegative element, will withdraw electrons from this OH bond. Okay? Because it is withdrawing electrons from this OH bond, this hydrogen becomes bare. That means it can be easily lost. So that is the first reason for the acidity of carboxylic acids. Okay? Please always remember, whenever you talk of the acidity or basicity of a compound, the stability of the conjugate anion or cation is very, very important. You know, if you are talking of acidity of carboxylic acids, the stability of conjugate base. Similarly, if you talk of basicity, the stability of conjugate acid is very, very important, right? Now, when the carboxylic acid exhibits acidic character, the corresponding anion formed will be the carboxylate ion, right? This carboxylate ion is stabilized by resonance. The difference here is that the stability of the carboxylate ion is much higher than that of carboxylic acid, which is responsible actually for the acidity of carboxylic acid. Carboxylic acids are acidic because on losing proton, they are forming carboxylate ion, which is more stabilized by resonance than carboxylic acid itself. You can see I have shown the resonance structure for carboxylic acid also. Carboxylic acid is also showing resonance. But what is it that makes the carboxylate ion more stable by resonance? It is the number one. See here, you have charge separation here. Okay, those canonical forms where you have charge separation are not highly stable. Whereas in case of the carboxylate ion, there is no charge separation. You have a uninegative charge here. Okay, so plus very importantly, you have two similar canonical forms. The two canonical forms are similar. They're exactly the same, right? Which is responsible for the increased stability of the carboxylate ion. The third very important point here is that the negative charge in case of the carboxylate ion is residing on the highly electronegative oxygen, right? If the negative charge resides on the electronegative atom, it will be more stable, right? So these are the 3 points which are responsible for the acidic character of the carboxylic acid. The minus I effect, because of which oxygen acquires a positive charge, the resonance stabilization of the carboxylate ion, the similar canonical forms, plus the fact that in the stabilized carboxylate ion, it is the electronegative oxygen which is carrying the negative charge. Okay? All right. If you compare this with alcohol, yeah, the corresponding alkoxide ion which will be formed on ionization has a R group attached to oxygen, which is offering plus I effect. In fact, it is increasing the electron charge density on the oxygen, whereby destabilizing the alkoxide ion. That is why alcohols are very, very weak acid. Except for methanol, all the alcohols are weaker acid than water also. So please remember that. Okay. Regarding phenols, if we see the phenols, I will write the structure and explain. Again, you have resonance. Because of resonance, what happens is the lone pair of electron and oxygen are getting delocalized onto the ring. Because of which, again, oxygen acquires a positive charge, right? And because of this positive charge, what happens? Again, oxygen will withdraw electrons from the OH bond. And again, this proton gets bare and it can be easily lost, right? So that is the reason for the acidity of phenols also. The first point. The second point is, what is the corresponding base which is formed? Phenoxide ion. Phenoxide ion is also stabilized by resonance. Yeah. Like we have written 5 resonance structures for phenol, we can write exactly similar way 5 resonance structure for phenoxide ion also. I will write only 2 of them. The remaining in the similar manner you can complete. Right? Now the question that we should ask ourselves is that resonance energy depends upon number of canonical forms. Higher the number of canonical forms, higher is the resonance energy released, more stable is the molecule. Okay? The carboxylate ion has 2 resonance structures, whereas the phenoxide ion has 5 resonance structures. Even then, carboxylic acid is a stronger acid than phenol. Can you tell me why? The reason lies in the stability of the sigma complex, the stability of the canonical forms. I told you that, yes, exactly. The negative charge in case of phenoxide ion, except for one structure, that is the first one. It lies on the less electronegative carbon. That is why the canonical forms are not stable, as is the case in the carboxylate ion. Okay? So it is this fact which makes carboxylic acid stronger acid than phenol. Okay? You can see in the slide here, I have shown the ionization of alcohol. You can see that the direction of equilibrium is lying mostly towards the left, right? Because alcohols are actually weaker acids than water, except for methanol, I've told you just now, right? In case of carboxylic acid, being a stronger acid than water, it will ionize in water and it will give it proton. Water will act as a base, it will take the proton and it will form the hydronium ion. Correct? Resulting in the formation of resonance stabilized carboxylate ion. Now what I have shown in this slide is the stability difference between the alkoxide ion and the carboxylate ion. You can see there is a huge difference in energy between the alkoxide ion and the carboxylate ion, and the difference is because of resonance. Na? Because of delocalization of the minus charge, what happens is effectively there is only a half negative charge residing on each of the oxygen, right? The full negative charge gets delocalized. In the next slide, you will see that structure. So the actual structure we see is like this. So effectively, there is only a 50% negative charge residing on each of the oxygen. Please remember, as the negative charge residing on oxygen goes on decreasing, the acidity of that particular compound will increase. Why I'm telling you this is, if you have to compare the acidity of, say, sulfonic acids, where there are 3 oxygens, with the carboxylic acids, you will find sulfonic acids will be stronger acids because there are 3 oxygens. Follow what I'm saying? So let us see the next structure. Yeah, that's the orbital picture, where the 2p orbital on carbon, this here, will partly overlap with the orbital on this oxygen, and also partly overlaps with the oxygen on this atom. Okay, giving it a half negative charge on each of the oxygen atoms, right? Next, we will discuss the effect of substituents. Oh God. अभी कुछ नहीं. Yeah. So what we are going to do is, we are going to split this discussion into 2 parts. First, we will see what is the effect of electron donating groups on acidity of carboxylic acids. And next, we will see the effect of electron withdrawing groups on the acidity of carboxylic acid. Now, let me take one example here first. So by rule, please always remember, an electron donating group will decrease the acidity of carboxylic group, and an electron withdrawing group attached to the adjacent carbons will increase the acidic character of the carboxylic group. Let us first see the effect of electron donating groups. You see that the acidity follows the order as the carbon chain length or the number of alkyl groups attached to the alpha carbon go on increasing, the acidic character goes on decreasing. You find in fact that amongst the aliphatic carboxylic acids or the aromatic carboxylic acids, formic acid is the strongest acid, which has a pKa value of about 3.76. Okay. Now, the moment you replace this hydrogen by an alkyl group, what happens is, this alkyl group offers plus I effect, Because of this plus I effect, what happens is the electropositivity of this carbonyl carbon is decreasing. Because the electropositivity of this carbonyl carbon decreases, this lone pair of electron on oxygen will not be able to enter into resonance with the ring. Okay, so there is a decreased tendency for this lone pair of electron to enter into resonance. If this lone pair of electrons is a decreased tendency for this lone pair of electrons to enter into resonance, means less positive charge on this oxygen. Less positive charge on this oxygen means lesser tendency to lose the proton. So electron donating group is discouraging the lone pair of electron on the OH group, number one, from entering into resonance with the ring, and more importantly, if you consider the stability of the conjugate base, the formate ion will be much more stable as compared to acetate ion, again because of the same reason. Again you have plus I effect, the electropositivity of this carbonyl carbon is less, because of which again you have decreased delocalization of this negative charge. So the effect of the electron donating group or electron withdrawing group is twofold. Number one, it affects the tendency of the lone pair of electron on the OH group from entering into resonance, and number two, it is affecting the stability of the carboxylate ion. In case of an electron donating group, the stability of the carboxylate ion is decreasing, right? ठीक है ना? So as the chain length increases, the acidic character will go on decreasing. ठीक है बेटा? Let us go to the electron withdrawing group. Now I just now said if you have an electron withdrawing group attached to the alpha carbon, for example, which is withdrawing electrons by minus I, it will generate a positive charge on this carbon. This will in turn polarize this carbon. It is increasing the electropositivity of the carbonyl carbon, whereby facilitating the lone pair of electrons to enter into resonance. Facilitation means oxygen will carry a higher positive charge, means the proton is more acidic, it can be easily lost. Okay? On the same lines, because of the increased electropositivity of this carbon, the stability of the carboxylate ion will also increase. It will be more stabilized by resonance, right? Okay. Now, when considering the electron withdrawing group, we'll come back to this slide later. There are, a few things that you have to understand. The first thing that you have to consider is the nature of the halogen or the nature of the electron withdrawing group. A stronger electron withdrawing group will increase the acidic character more than a weaker electron withdrawing group. Let's go back to this slide here. Here, I have shown the order of withdrawal of electron here. So CF3 will be the strongest electron withdrawing group, followed by nitro, then cyanide, then fluoro, chloro, bromo, iodo, and phenyl. This is the order of withdrawal of electrons by inductive effect. Okay? So stronger electron withdrawing group, because of those two reasons again, will increase the acidic character more, right? Next is the effect of number of halogens. As the number of halogen substituents increase, the acidity will go on increasing, because again those two reasons. For example, if I have Here there is only one chlorine attached to the alpha carbon. Here there are two chlorines attached to the alpha carbon. Okay, because there are two chlorines attached, the electropositivity of this carbon will be more. So the acidic character of this dichloroacetic acid will be more than that of monochloroacetic acid. So this will be a stronger acid as compared to this, right? With increasing number of electron withdrawing group, the acidic character is increasing. Okay. The third is the position of the electron withdrawing group. As the electron withdrawing group moves away from the carboxylic group, the acidic character will decrease. Again, because the inductive effect dies beyond C2 carbons. You know that? What I mean here is, as the electron withdrawing group moves away, the acidity will go on decreasing, right? The next is the effect of hybridization. If the alpha carbon attached to the carboxylic group is sp3 hybridized, and you change it to an sp2 hybridized, the percentage S character is increasing in an sp2 hybridized carbon. So sp2 hybridized carbon is more electronegative as compared to sp3 hybridized carbon. So as the S character on alpha carbon increases, the acidic character will go on increasing. Means if I have this acid, or if I have this acid, will be a stronger acid than this, right? And if I change it to an sp hybridized carbon, the acidity will further increase, right? And the last of the things that we discuss here is the comparison of strength of aliphatic acids with those of aromatic acids. You see the trend here I have written. Formic acid is most acidic, okay, followed by benzoic acid, and after that all the aliphatic acids will come. That means benzoic acid is only weaker acid than formic acid. That order is very important, you have to remember. Okay, we will justify what makes benzoic acid a stronger acid than all the other aliphatic carboxylic acids. Okay. Now see, hydrogen very weak, negligible inductive effect, right? When you come here, the benzene offering offers plus R, right? Because of the plus R effect, what happens is the electropositivity of this carbonyl carbon is decreasing. But benzene ring is not only offering the plus R effect. Besides the plus R effect, it offers also minus I. And what is that minus I due to? That minus I is due to the presence of this sp2 hybridized carbon, right? So plus R hai. Besides that, you also have minus I effect, which is acid strengthening. Plus R, acid weakening. Minus I, acid strengthening. Very good. Now, but here what happens when you go to acidic acid? You have only plus I, which is acid weakening. So the net effect of these two, plus R and minus I, is that the electropositivity of this carbon is more than that of all the other aliphatic carboxylic acids. That is why you find that benzoic acid will be a stronger acid than all except formic acid, where there is no inductive effect. Follow my point? Now, one more thing I want to tell you here is, now if the benzene ring is directly attached to the carbon, it can offer plus R effect. But what if the benzene ring is not directly attached to the carboxyl carbon? For example, the case of phenylacetic acid. This is acetic acid, and the other compound is, see, one hydrogen has been replaced by phenyl group now, so this is called phenylacetic acid. Okay. If you have to compare the acidity of acetic acid with that of phenylacetic acid, now because it is not directly attached to the carboxyl group, there is no plus R effect. But besides plus R effect, we have learned it has minus I, right? So in this case, the only effect that is operating because of benzene will be minus I. And here you have plus I, which will make phenylacetic acid a slightly stronger acid than acetic acid. Is that okay? How much time? 5 minutes. Clear? Let's take up a few questions. We have time for a few questions. Let us look at the first question. Bilkul, very good. Benzoic acid, the first reaction you have phenol. When you reacted with zinc dust, it will give you benzene. And when you reacted with, what reaction is this? Fiedel-Crafts alkylation, right? So you would form toluene. Okay? Which on oxidation? Will give you benzoic acid, right? The next question, please. Please see what is happening in this reaction. What kind of a compound is this? What is the functional group here? It is a, what kind of ketone is this? It is a methyl ketone, right? And what is happening in the reaction? You have a methyl ketone which is being converted into carboxylic acid having one carbon less. So what reaction is this? Haloform reaction, right? ठीक है बेटा. I think we have time for one last question. We will not take the third question because that we have not discussed. That is aromatic carboxylic acid. That will be done in the next class. Okay, we will take this question on aliphatic carboxylic acid. This trend we have already discussed. Okay, let us see this question. Two bromobutanoic acid, 3 bromobutanoic acid, then isobutanoic acid, then N-butanoic acid. See here, you have two different types of groups here. That is why I have written them separately. You have one electron donating groups attached to the carboxyl group, and the other category is the electron withdrawing group attached to the carboxyl group. Now we have already learned electron donating group decrease the acidic character. Now you see the chain length. Here you have a isopropyl group, right? And you have an N-propyl group attached to the carboxylic acid. Isopropyl group offers a stronger inductive effect as compared to the N-propyl group. So this will be a weaker acid than normal butanoic acid. So this will get number 4. This will get number 3, right? Let us come to the next two compounds here. Again, I told you, as the electron withdrawing group goes away from the carboxylic group, the inductive effect is decreasing, right? So here you have halogen attached to the alpha carbon, and here you have halogen attached to the beta carbon. That means an electron withdrawing group increase the acidic character, right? So this will be a stronger acid than this. So this will get number 2 and this will get number 1. So this will be the strongest acid amongst the 4, right? Any question you have? You want to ask anything you have not understood? I think that will be all for today. Thank you.